Hello, everyone. We're going to get started with some hypothesis testing to lay the foundation for the work that's to come. So we're going to be talking about hypothesis testing, confidence intervals, and other forms of inference. We're basically making educated guesses based upon our sampling and the data that we collect. And this will be very helpful for you for the unit coming ahead and for your final project. So what we're going to first take a look at here is the gender discrimination claim, where we have 35 people being promoted out of 48. We have 24 males, 24 females. Of those 24 males, 21 were promoted, 3 were not. 14 females were promoted, and 10 were not. So if you take a look at these proportions, and the little hat right there, that means that it's a estimator. That means it's based on a sampling that we're doing, a sample proportion, because we don't know the true proportion of all males and females. So we're going to do a sampling, and what we found out is that the sample for males being promoted was 88%, whereas the percent of females was only 58%. So the difference is quite significant, but we have to test to see if it's significant enough to support the claim that there's gender discrimination or that females are not being promoted as often as males are. So the little hat, again, this little hat right here means that it is a statistic. That means a calculation based on our sample. We're trying to estimate the true population of the entire company in this case, let's just say. All right, so now promotion and gender, well, they should be independent. If they are independent, then we have no discrimination. Remember, independent means that given that it's a male or a female, the chance of being promoted should be the same. So independence is a good thing here. And if they are independent, then there should be no gender discrimination. However, if the sample, if the proportion is significantly off based to a certain threshold that we will study, it could be off just based on chance. The next sample could be more females be promoted than males, so we don't know that. So what we do is we assume that there's no problem, and that's called the null hypothesis, H, or the little 0 on the bottom, H naught, okay? And so we're going to take a look at that. Now, the other scenario is that these proportions are, the gender promotions are not dependent. If they're not dependent, I mean, if they're dependent, that means that the gender is a factor in whether or not the person gets a promotion. So there is gender discrimination. So dependence is a bad thing here. That means that your chance of getting a promotion depends on your gender. So the alternative would be to the null meaning it's no problem, would be that yes, indeed, females are not promoted as often as males. So we need to take a closer look to see which of those scenarios is the most accurate, and that's called inferences process. So take a look at some data, differences in promotion rates, positive and negative. Looks almost normal, so can't tell a difference from this sample. It doesn't seem to be reflected in that data. Taking a look here, so we have a nice, pretty normal curve right there. Let's go back. So, I mean, 30% difference is pretty significant. I think it was 88% to 58%. Now, in order for there to be no gender discrimination, that difference has to be due to just random chance based on the type of sample that we had. We just happened to have more males in the sample that got promoted, whereas future samples could have more females. We don't know that, but that difference is pretty significant, so it's worth further study to take a look. So we're going to take a closer look. So remember, H naught right here, that is the null hypothesis. That means that everything is normal and there's nothing fishy going on, that there's no gender discrimination. The alternative hypothesis would be that something is going on. Presents that's what we're actually looking for. So we're trying to disprove normality, or not normality, but everything's status quo. It's called status quo, and thereby favoring an alternative, meaning that there is gender discrimination in this case. So let's take a look. So we assume that the null hypothesis is true, and then look for data that leads us in that direction. So if the data is not significant enough, then we just say that we stick with the null hypothesis, stick that everything is okay. So the data has to be significant enough to get past that threshold, and we're going to quantify that in the days ahead. But if it does get past that threshold, we're going to reject the null, reject status quo in favor of the alternative, meaning what we're actually intimating that there is gender discrimination or testing for. So we're going to formally look at hypothesis testing in the days that come ahead. All right, we're going to take a look at a specific example here. So let's assume we have a 95% confidence interval. That means that we are 95% confident that the true amount of average number of relationships, dating relationships, college students is somewhere between 2.7 and 3.7. So this is from an early example early in the course, exactly where, based on this confidence interval, is that data strong enough to support the fact that college students on average have been in more than 3 exclusive relationships? So we have our data. This is our confidence interval. That means 95% of the time, this interval is going to contain the true parameter, which is a population parameter, which is p without the hat. Okay, the parameter, which is p, is going to be 3. This is strong enough evidence that 95% of the time it occurs in here. Well, let's take a look. Well, what would we do? The null would be status quo. The average is 3 exclusive relationships. And the alternative would be, no, it's bigger than 3. All right, mu is greater than 3. That means that college students have been in more than 3 exclusive relationships. That's what we're looking for. That's what we're seeing. So we'll take a look. Well, what do we see? Well, since 3.0 is in our null hypothesis, it's quite possible that that's due to chance. So we can't reject the null hypothesis. We failed to do what's called fail to reject. So since the null is in the interval, meaning that 3 is inside here, we do not reject the null. So we cannot say that it's the average number of relationships is greater than 3. We just stick with the possibility that it could be 3. All right, this is just a fast approach to it. But what we're going to do soon is we're going to calculate a p-value, and that p-value is going to be very significant to decide whether or not we're going to accept the null or not, or reject the null. See what this means. The p-value means, get this. This is a really huge definition here. The p-value is the chance that we could get some data that looks extreme, but really the null is still true. In other words, let's just we took a sample and the average number of relationships was 4 or something like that. Well, that could happen. And the average number is still 3, but the chance is pretty small. Well, that chance, an exact chance, is how likely it is that we could just get a sample that has non-representative information that doesn't tell a true story. It's like saying somebody's a 90% foul shooter, but they made 7 out of 10 in a given game. Now, what's the likelihood they make 7 out of 10 in a game, given that they really are a 90% free throw shooter? Well, that's the p-value, and we're going to quantify that and make decisions. And we'll do that with our graph. So I'll take a look at another sample here. It's just saying, again, this is just an overview. We're going to get to specific numerical problems later on once we have this foundation. But let's say that we have some college students who applied to college. They were sent a survey asking how many colleges they applied to. The sample was 206. Say the average number of students at colleges that students applied to was 9.7, and the standard deviation was 7, which is quite large. The College Board wants to basically encourage counselors to recommend that each student apply to 8 colleges. So this might be of importance to you since many of you just apply to college. So does this data significant enough to support, I don't know why there's Duke in here, but that this particular college is higher than the average because they had 9.7 as their average. I guess Duke was supposed to be here, might have been a typo. But is that enough information? Let's take a look. Well, which one of these assumptions do we not need? Some of this you're going to get from my open math when you read it. Just applying it here. So students, typically, yes, students in a sample should be independent of each other, obviously, because otherwise your data would not be significant if it's conditional probabilities. Sampling has to be done randomly. You don't go to the library and ask whether people want longer library hours, just like our old test that we talked about, the test question. This is the key concept we're going to talk about, that is that sample size should never be more than 10% of the population. And the reason why that is because the bigger the sample size in relation to the population, the fewer samples you can take from that population, and therefore it will be less and less normal. The smaller the sample, the smaller the sample size is a little bit smaller, under 10%, you can take an infinite number of those samples, and therefore our data is going to be more accurate, representing normal distribution. We'll talk more about that when we talk about the central limit theorem. We don't have to have 10 successes and 10 failures in the sample in order to conduct a hypothesis test. Yeah, we should try to avoid extremely skewed. Yes, extremely skewed populations are not going to be that reliable. However, the central limit theorem is going to tell us that if we have a sample size that's 30 or higher, even if the population is not normal, that we can assume normality. We're going to learn that in the days ahead. Okay, one of the most important values in statistics is called the p-value. If you learn nothing else in this course, that's one thing to remember, is p-value. So what does p-value mean? It's actually the probability, get a little pointer here again, it's the probability that we could observe some data in our sample that's not truly representative, but that the null is still true. That's what it really means. The null is still true, even though we get some aberrant data in our sample. Okay. The probability of observing at least, okay, so that means that, as I said before, somebody being a 90% foul shooter and getting 7 out of 10 in the game, could that happen? Yeah. But does that happen that often? Probably not. Or maybe that person is not a 90% free throw shooter. So a p-value is the chance that the null hypothesis is still true, even though we found data that was not what we expected. Let's put it that way. So a typical p-value would be like 5% or under. So it's like you're driving 60 miles down Route 81. Officer pulls you over and says, "Oh, I don't really do it this often. I just wasn't paying attention. But almost all the time I drive under 40 miles an hour." Well, the officer's got to make a judgment based on that. And if you have like 3 or 4 tickets from the past, well, he might not believe you. He'll think the null is not true, that you're a good driver, and he'll reject it. So there's p-values around you everywhere. So we want a p-value under 5%. That's key. And if it is, it's very unlikely that you're going to observe data. That means that's good. That means we can reject the null hypothesis in favor of the alternative. That's what we want to do. We want to reject it. So if we get under 5%, that's pretty significant. It's an under 5% chance that the null is still true. So we're going to reject the null in favor of the alternative. That's the basic idea here. So when our p-value is high, so higher than alpha, alpha is going to be our threshold. Okay, so this alpha right here is going to be a threshold for our p-value. So typically, if it's below 5 or 5%, we're going to reject the null, the status quo, and accept the alternative. And if our p is high, that means that there is a realistic chance that this sample could be not what we expect, and that the null hypothesis is still true. So if that's high enough, then we don't accept the alternative. We go with the status quo. We don't reject the status quo. So that's the significance of p-value. Above, we do not reject. Below 5%, we do reject. But that 5% could be different. Some problems that this alpha here, depending on how strict we want to be, we want to go to 2%, 1%. That's going to be more statistically viable if we say p-value of 0.01. That means we're really, really sure that the data that we found was not that the null is not true. Okay. So just to round out that problem before with the average number of college applications at Duke University, I think it was, just to round that out, their average was 9.7 and the typical average was 8.0. So what's the probability that the average really is 8, even though Duke's average was 9.7, maybe their average is higher than normal. So if we calculate that probability using a standard normal table, assuming normality with the sample, we get 0.0003. So that means that it's very unlikely that the average really is 8, that it's probably higher than that. And that's what they found out from that example. We'll proceed with some more examples in the next video. Sorry this is so long. We're going to get to some numerical problems shortly, but this is what we need to do for now.